So, hello everyone. So, today we'll start our tutorial. So, today's tutorial 11, tutorial 12. So, okay. So, for this tutorial, the mostly we'll be focusing on some advanced problem in both like from thermodynamics as well as from statistical mechanics. So we'll do some problems from like chemical potentials, from starting from chemical potentials to from the partition function of its statistical mechanics. So basically, these types of problem will be there in today's today's tutorial session. So let's start from the question one actually. So okay, so. One, yes, and chemical terminal expansion process during which the change in entropy is to be delta S. If the universal gas constant is not will work done by the gas is given by infinite P delta S by NR option B NR delta S option C EV option D P delta S by NR. Okay. So the problem is a sample of an ideal gas with the initial pressure P and volume V is taken into an isothermal expansion process during which the change in the entropy is to be delta. So what happens here that as this is isothermally expanding, so because of that process, like at the initial pressure P and volume V, so because of that the change in entropy as the gas is expanding, so because of that the change in entropy is given as delta S. Now by considering the initial gas constant is R, we have to find out what is the work done by the gas. So we know that for the work done by an ideal gas for a quasi-static, that means the reversible expansion or compression is given by this. So firstly, what is the definition of work? So work done Yes. Static. What's static means? Reversible, right? Reversible expansion and variation is, so this is given work done Vi by Vf PdV. Okay, this is the work done. Now here, now, so now here it's already mentioned that the gas is basically an ideal gas, right? So what you have to use the ideal gas for it. So from there, so we know for an ideal gas, the equation of state is UV equal to nRT. আমি না এটা একটু পরে কল করছি বুঝলি তো, কারণ আমি যে ক্লাস চলছে না এখন, বুঝলি তো, চেঞ্জ হয়ে যাবে। হুম, ঠিক আছে। So, so the for an ideal gas, this is the equation of state PV equal to N of T. Now, from here, the pressure would be P equal to nRT by V. Okay. So, pressure is nRT by V is given. You already know it. That is coming from this equation of state. Now, if you substitute it in the so if you substitute in one, what we got? We get W equal to VI by VS nRT V dV. Okay. Now nRT VI by VF dV by V. Now if you do the integration, this will simply gives you nRT ln VF by VI. So this is the general definition of work done. So by given the condition is that this is a isothermal process. Isothermal means the temperature is constant here. Okay, given by considering that fact, if you want to calculate the work done on the system, you just simply use the general formula of work. Then from there, substitute the expression of P into the expression of work done, and from here there, if you do the integration, this will gives you the total work done, where the temperature is constant. Okay. So now, what you can do now, this is the, so we got the expression of the work done. Now, now the delta is okay. So let me so now what we can do that. Now this is work done, but in the problem we have to find this work done in terms of delta S. Delta S means the change in the entropy. Okay. So how we can do that? So in order to do that, what we can do? So so what we can do? We use the first law of thermodynamics here. Okay. So according to the first law of thermodynamics. So according to the first law of thermodynamics, what we know that is d equal to dq plus dw, right? So now here, what is du? Du is Cp. Here we are considering the fact the pressure is so basically this specific heat. Okay, like depending upon the condition, you can take C as constant at pressure. That means specific heat at constant pressure, or it can be calculated at constant volume. In that case, it would be specific heat at constant volume. So for the generality case, we are taking it as C only, which is the specific heat. So d equal to basically C dt, dq equal to TDS and dw equal to PdV. That you already know, right? Actually, dw, PdV, the dw expression you already know actually. So if you do the integration, then what you got? Delta U equal to delta Q plus delta W. Okay. Now here delta W already know, that is this nRT ln VF by VI, right? Now next thing is delta Q. Now here delta Q, what is delta Q? Delta Q is TDS, so delta Q would be TDST delta S equal to nRT ln VF by VI. Now here delta U is CVDT. Now we know that already. During this process, the temperature change in temperature is there is no change in temperature, right? So dt is basically is 0, right? Which actually means du is also equal to 0, right? So this is one thing you have to consider, right? As the temperature change is very small here, so change in the internal energy also should be equal to 0. Now, so now what you can do, you can write that means ln Vf by Vi as T delta S by nRT. Now here, from here we can write work done as nRT ln Vf by Vi. Now, so this is the work done, right? So let's give a number to this equation. Equation 3. Okay. Now here, this is the expression of the work done that we got earlier. Now here, from here, if you substitute this expression, like substituting three in expression of work done, what we will got? We get W equal to nRT by T delta S by nRT. Okay, now nRT will cancel, we will got T delta S. But in the expression there is no T delta S is given. That means you have to substitute like the things once again. So for that, what you can do, what is like, you already know that from this gas equation, PV equal to nRT, right? Now T we can write as PV by nR. Okay. Now if you substitute this thing here, what will be getting? W equal to PV by nR into delta S. So this would be the work done. Okay. So this is how you can calculate the work done. Okay, like this is the expression is no this. The correct answer would be this. So what we have done? So here in the question it's mentioned that A sample of an ideal gas with initial pressure P and volume B is taken into an isothermal expression process during which the change in entropy is to be delta S. Now, if the universal gas constant is given R, then the work done by the gas you have to find out. Now, for that, what we can do, we first develop the work done. This is the basic formula of work done. Now, from here, what we have done, we have used the ideal gas equation, because here the change in volume or pressure, whatever you take, we have to implement that thing into this work done. So for that we are using the ideal gas equation. Now we want to write the work done in terms of change in volume. So for that we have write this pressure in terms of the volume. Now from here we have substitute the pressure here. This is the expression of the work done. Now if you do the integration, the work done for this case, remember in this case the temperature is remain constant. As you can see, it's mentioned the process is an isothermal process basically. So by given this fact, now if you calculate the work done, so work done simply gives you nRT ln log natural log Vf by Vi. Now from here, so the thing is, now from here, if you now from here, now we have to write this thing in terms of the delta S. Okay, delta S means change in entropy. Now for that, we first write the first law of thermodynamics, that is d equal to dq plus dw. That means change in the internal energy should be equal to the change in heat plus the work done by the system. Now from here, du you already know, c is a specific into dt, dq equal to tds, and dw is work done is nothing but the nRT ln Vf minus Vi. Now if like after substituting all of this thing here, so after that we will be getting T delta is into nRT ln Vf minus Vi. Now from here ln Vf by Vi. Now what we do, we will do some mathematical tricks here. Okay. So we write this ln Vf by Vi in terms of T delta S by nRT. So we got the expression of ln Vf by Vi. Now what we do here, we then so in the work done expression you already know the work done is written in terms of nRT into ln Vf by Vi. Now what we do is simply substitute this equation number 3 here into the expression of work done. Now if you substitute this log term here, you will get this modified expression of the work. Now if like after cutting nRT, you will be remain with work done equal to T into delta S. Now, but in the answer, as you can see, this answer is not given. So we have to do further substitution here. So for that, what we have did, we know already the ideal gas, equation of the gas, equation of the state for a gas. Now from here, we write the temperature in terms of PV by NR here. Now if we substitute this thing into the work done here, after doing that, we will get this expression of the work done, which is basically given as the in the answer, as you can see, option number D. So this is the correct answer. So this is how you should calculate the work done of the system. Okay. So now I go into the next question. So question 2. Question 2. Cp greater than Cv, where Cp is specific heat of a gas at constant pressure, and Cv is specific heat of a gas at constant volume. Because at constant pressure, because at constant pressure Option A, the attraction between the molecules is larger. Option B is the coefficient of expansion differs. Option C is work is done by the expanding gas. Option D is none of the above. So before solving this problem, let me just derive like the how this Cp is greater than equal to Cp condition is basically coming up. So that we will be taking as a starting point. Okay, like how this Cp by Cp is greater than Cv, how this condition is basically coming, and from there we'll be checking these facts, the 4 facts that's are given here. So out of these 4, which will be the correct one? Okay. So in order to do that, what we are first we like the our very famous first law of thermodynamics. Okay, so first law of thermodynamics. So dq equal to du plus dw. Now here let me write in terms of work done. dq equal to du plus dw. Okay. So this is you already know the first law of thermodynamics. That dq is basically change in heat. Q is the heat. Du is change in internal energy, and dw is the work done. Okay. So these are the given things. Okay, so now okay, so now as it's given, so now what you can do, uh, so so what you can do, so in the question it says it's constant volume. Okay, so we will first what's our main goal would be first to derive the specificity at constant pressure and constant volume. Okay, so first case we would be considering at constant volume. So for this, dv will be taking as 0, dq equal to du plus dw. Now dq would be du. Du already know is cv dt, right? So cv would be simply, cv means specific heat at constant volume. Okay. So this is the cv thing. Okay. Now cv you can write it as dq dt at constant volume or du dt. Same. Just you have to divide this dq by t or dq by t, whatever. So now, so okay, so for an ideal gas, like for n mole of ideal gas, that means du should be so Cv dt. So for n mole of ideal, so this is the expression of du, like in terms of the Cv space. We actually need this relation, okay, for later use actually. So now this is at constant volume. Now at constant pressure. So at constant pressure, the gas expands. As we know, at constant pressure, the gas expands is basically is the work done. Okay, so the gas expands is the work is done. Now here, so dq basically du plus pdv. Now here, as here this is at constant pressure, right? So we cannot simply make pdv equal to 0 because the pressure is constant. So that means there will be change in the volume here, right? So that means pdv term is not 0 here. Okay. So this means that this term is simply not equal to 0. Unlike the previous case, like at constant volume, where we make the work done is equal to 0 as dv is equal to 0. So now what you can do from here, so pdv is not equal to 0. Now what you can do that you can write pdv equal to nr dt. Right. So now dq equal to ncv dt plus nr dt. Okay. ncv dt, how we got? We got it from here, this equation over here, this limit 1. So this is the equation is 2. So let's take it as 2 limited 2 limited 3. So now after substituting 3 and 1 at equation 2, we get this simply. That is dq ncv dt plus nr dt. Now from here you can write dqp dq as ncv plus r dt, right? Now from here cp you can simply write it as dq by dt. That means ncv plus r. So this is for n mole. That's for like for n equal to 1. Like we are considering for n equal to 1 case would be cp equal to cv plus r. Sorry, cv plus r. So that means cp would be greater than equal to cv from this, right? So this is how you can show. This is also a very important relation, cp minus cv equal to r. So from here you can easily from first of thermodynamics you can easily show that how the cp is like prove this fact, cp will be always greater than cv. So for that what we have done here, let me just briefly explain. So we started from our first law of thermodynamics, started from the very beginning, and now from there what we have done, so starting from the first law of thermodynamics, so first case we are considering the at constant volume, right? That means dv equal to 0. So dq equal to du plus dw. So dq equal to du. So dq equal to cv dt. Now cv you can write as dq dt at constant volume. dq dt is nothing but du dt. Now du you can write as an n cv dt. Now from here what you can do, as the at constant, so this is the case at constant volume. So this should give you expression of du in terms of n cv dt. This relation we actually have to use in later cases. Now at constant pressure case, okay, so constant pressure case the gas expand work is done, and for that case, as the gas expand, because pressure is constant here, so volume will be changed, so this term would not equal to 0. And PdV is already we know from the ideal gas equation, PdV equal to nR dt. So this basically comes from the fact that PV equal to nRT. Now if we take the derivative both side, PV T into nRT, this gives you basically VdP plus PdV equal to nR dt. Right. Now here as the pressure is constant, this term would be equal to 0. This basically gives you PdV equal to nR dt. Here in the right hand side, as nR both are constant, so only thing that will change here is the t term, right? So PdV is nR dt will coming like this. Okay. So we got PdV equal to nR dt here. Now from here what we do, we got the we got the we got du, expression of du as well as PdV, right? Now I will simply substitute this thing in here to get the Cp. After substituting this here, we get dq equal to ncv plus r dt. Now Cp you already know, specificity is nothing but dq by dt. So if you do the dq by dt, it gives you ncv plus r. Now for case of 1 mole n equal to 1, Cp would be simply equal to Cv plus R, which basically satisfies Cp would be greater than C. So this is how we can calculate, okay, specific heat. Cp minus Cv equal to R. Now as by proving the fact Cp would be greater than Cv, next thing what we can do, so we have to consider what would be the correct case over here. So basically the question is, what is asking that the specific heat at constant pressure, that means Cp, is greater than specific heat at constant volume Cv for an ideal gas. So which means that which of this thing is the correct answer? So let me write that thing. So what is basically specific heat is? So first let me write this things. So specific heats, what in generally specific heat what means is the amount of heat required to raise the temperature by unit temperature of a unit mass of a substance by 1 degree. Okay. Now at constant volume, now if you consider it as at constant volume, so we know that so specific amount of heat, so we know dq equal to du plus dw, right? So from here, as you can see, at constant volume, as you know, delta V is equal to 0, right, at constant volume. So this actually means no work is done. Okay. No work done is there. So that basically means all the heat goes to increase increasing the internal energy. So as at constant volume, so dW term is basically becomes 0. So dQ equal to, that means du, which means whatever heat you are basically supplying into the system, the whole heat basically converts, whole heat basically helps to increase the internal energy of the system. Okay. Now, so this is one thing is there. Now next thing is that at constant pressure, uh, now this is a constant volume. Okay. Now what happens at constant pressure? At constant pressure, now at constant pressure, what happens that the gas expands. Okay. So as constant pressure, so that means the gas expands, right? And gas expands means delta V would be simply not equal to 0, right? So that means some heat. So see, this is the heat. Some portion of the heat goes to work done by surroundings. That basically means gas expands. Some part would be simply goes into raising the internal energy. So the heat basically divides into two parts. One part would be basically one part would be using the work done by the gas, and one part would be using to raise its internal energy. So this is the two way that heat would be used. It would be used now. Uh, so that in the question, so in the question is mentioned at constant pressure. So at constant pressure, this would be the correct answer, right? Work done by the expanding gas. Okay, right? If it's a constant volume, then everything would be simply the every part of the heat would be simply used in the increasing the internal energy. But here, as the pressure is constant, so for that case, the work done is simply transferred into expanding the gas. Okay, so this the correct answer will be then option C. So this is it. Now we'll go to the question 2 is done. Now we'll be moved to the question 3. Okay. So question 3 is an electric current of 3 ampere flows through a rod of resistance of 10 ohm. It is being cooled by running water. It is being cooled by running water and is kept at a temperature of 300 Kelvin. The change in entropy per second at the resistance is zero point 0.3 joule inverse degree inverse. Option B is 3 joule inverse degree inverse. Option C is 30 joule inverse degree inverse. Option D is 0. So what is basically happens here? So electric current of 3 ampere flows through a rod of resistance 10 ohm. It's being cooled by running water and is kept at a constant temperature of 300 Kelvin. The change in entropy per second of the resistance is okay. So what actually happens here? Uh, so here what happens? So there is a current. So there is a wire. Okay. Inside the wire there is a resistance here. Okay. So what happens when the current flows? Normally current flows, nothing happens. But when this electron basically current basically is nothing but the electrons, right? Like whichever direction the electron flows, the current flows in the opposite direction. Okay. So when the current flows through these resistors, it will face some obstruction, right? So because of that, it have to do some work, like the electric currents has to do some work, right, in order to avoid that obstruction. That is basically the work of a resistance, right? So here in the problem it's mentioned that 3 ampere current is flowing and there is a resistance of 10 ohm is there. So now when this current flows through these resistors, as it is doing some work done, for that it would for that work done is simply actually basically converted into heat, right? Like from the first of thermodynamics, you already know this work done is converted into heat. And now here what is the main important thing is the heat is like this heat whatever producing in the resistor is instantaneously cooled by the running water. Okay. So for that, the temperature of this wire, this resistance, is kept constant at 300 Kelvin. So that means throughout the time, this resistance thing is kept at a steady state. Okay. So this is the important thing to be taken care of here. So first, what we will do here? First, we read whatever the information is given here. So current current I equal to 3 ampere, resistance R equal to 10 ohm, temperature of the resistor is at constant T equal to 300 Kelvin, and this whole resistor is by running water. So that means system is in steady state. So these are the information basically given. Look. Now from here what you have to do, you have to calculate what is the change in entropy. So first what you can do, you can calculate what is the power, like what is the heating power that comes, right? So we already know. Power is basically heat heat produced every second, right? So power is basically heat producing every second, because here we don't know the time, right? So we have to consider the whole thing that is happening. We have to calculate at unit time. Okay, what is happens at unit time? Okay, so at every second, I mean unit second, whatever the time unit you are using. So P for like you already know, like if the wire is there and resistance is R, if the current is flowing I, the total power would be I square R, right? This is the power. So this will be I square R. So I square is 3 square into 10, that gives you 90. Okay, so that means the power, so means that the heat that is producing every second would be 90 watt. So now what you can do, so now the main thing is like, so if the like we already, like in the problem it's already mentioned that the resistor is cooled, like every time it is cooled by using a running water. So as the resistor is cooled at all the time, so that means it's kept at a steady state. Okay. That means there is no net change in the internal energy of the resistor. So, which means that whatever actually means that whatever the heat that is produced by this resistor is instantaneously like immediately transferred into the surroundings. Okay. By using this by running this cooled water. Okay. So that means the whole heat basically transferred into the surroundings at each time. Okay. So whatever heat produced by the resistors instantaneously transferred into the surroundings. Okay. So that means the change in the entropy would be 0 for the case of resistor, and it doesn't retain any heat, right? For that case, the change in the entropy for the resistor would be simply 0. So let me write this thing. Okay. So as all generated heat is immediately transferred out to the surroundings, the resistor doesn't retain any heat. Okay. So for that reason, what happens? Uh, that means that the resistor temperature is basically kept constant, and which means that there is no change in internal energy. Okay, so that means delta is the resistor will be equal to 0. Okay. So delta is resistor, there will be no change in the there will be no change in the entropy. Okay. So delta is resistor will be simply 0. Now, so that means whatever heat is generated is transferred to the surroundings, which basically means there would be change in the entropy of the surroundings, right? Although there is no change in the entropy of the resistor, there would be some change in the entropy in the surroundings. Okay, so for calculating change in the entropy in the surroundings, so what basically happens here, like this is the wire, whatever dq is coming, it's simply transferred into the delta q is transferred to the surroundings. Okay, so how can I, like, this delta q, that means this delta q will be contributed into the surroundings, which results into change in the entropy of the surroundings. Okay, this is the important thing to consider here. Now, as these things, all these things are given, delta q is so okay. So now what you can do, now how from this dq, that means will be contributed into the change in the entropy of the surroundings. Now from this dq, how can you calculate the ds, like the change in entropy? So for that would be use our so we already know delta q is T delta S, right? So delta S should be simply delta q by T, right? So for this case, the delta S surroundings would be simply delta q. Delta q is 90 per second. Okay, 90, and the temperature is kept at 300 Kelvin. Okay. 90 by 300, which gives you 0.3 joule. Joule Kelvin per second. That's right. The second, because this whole power, like whole the current, like whole the work done is, or heat is supplied at per second, right? Because we are calculating the power. So that the whole entropy change would be also in terms of second per second, per unit time, how much entropy is basically gained by the surroundings. So this would be the amount 0.3 joule Kelvin per second. So the correct answer would be this one, right? Option. So let me just tell you what we have done here once again. So basically a current 3 ampere current is flowing here into this here, like into this wire where a 10 ohm resistance is there. Now what happens, the current is 3 ampere, the resistance is 10 ampere. So what basically happens here, when this current is flows through this resistance, it would face some resistance, right, when it moves to the resistor. So in order to overcome this resistance, it has to do some work, right? And we already know, like from the first law of thermodynamics, whatever work these electrons do ends up into the heat energy of the resistance. So basically, the temperature of the resistance would be would be raised. So okay, so And now now here the important thing is there, this resistance which is like this heated resistance basically cooled by running water. So what basically happens here, this resistor is cooled by running water. So because of that, this whole system is in steady state. Now the power, okay, so the power, from this all given information, what you can calculate the heat producing every second. That means the power. Power is already known, is nothing but the I square R. So it is 3 square into 10 gives you 90 watt. This is the joule per second. What means joules per second? That means the joule that is coming per second. Now, as this whole heat that is generated is cooled down, that means whatever heat is generated instantaneously thrown into the surroundings. That means the resistor doesn't retain any heat. That means there is no internal change in the resistor. That means there will be no change in the entropy of the resistors also, right? But what happens here, as the heat is contributed to the surrounding, there will be change in entropy in the surroundings. Okay, so to calculate that, we know that dq delta Q equal to T delta S. So from there we have calculated the change in entropy. Okay, that is delta surroundings into 90 by 300 0.3. So the change in the entropy of the surroundings will be 0.3 joule calorie per second. So this is how one should calculate the whole thing. Okay, that's it. Okay, so now we'll move to the question number 4. Just a second. Okay, so now in question number 4, 1 mole of an ideal monoatomic gas is taken from the state 24.6 liters on its own S star is S degrees this is state 1 to state 2. For state 2, the parameters are state 2, the definitions are 2 atm 320 delta G for the entire process is option A 90.8, option B 0.5, option C 335.8, option D 3.7. So this is the problem. So basically what happens here, 1 mole of ideal monoatomic gas is taken from state 1. Basically the gas is taken from state 1 and the properties of the state 1 is given. That means the 24.6 basically I think is the uh, volume of the gas, 1 atm is the pressure of the gas, temperature is 300 Kelvin, and this is the initial entropy, that is 81 joule per Kelvin. From this case, from this state, it is transferred into the second state, and for second state, only the pressure and the temperature is mentioned, that is 2 atm, that means 1 atm is raised to 2 atm, and 300 Kelvin to 320 Kelvin. Okay. Now for this problem, we have been asked to calculate what is the change in the Gibbs free energy. Okay, how we can solve this problem? So from the thermodynamic potential point of view, as we know, thermodynamic potential. So delta G we know is delta H minus T delta S. This we know, right? Like this is the change in Gibbs free energy. Delta H is change in enthalpy. T delta is change. Delta is change in entropy. Fine. So basically, you have to calculate these quantities. So how you can do that? So for that case, let's start from computing the delta H. Okay. So delta H is this, right? H is U plus PV. Now for an ideal gas, U is the internal energy, right? Internal energy. And PV already is nothing, pressure and volume. So now from here, so U is, so here for an ideal gas, U is basically NCV T. How it's basically coming? That is basically, so this is coming. So let's so du already know is PdV, right? Now for if the temperature is remain kept at constant, right? Or like for an like for this process, the volume is kept at constant, right? The pressure and so du, that means we already know dq plus dw, right? Dw is 0 because pdv is 0, because you can see for this process the volume is kept at constant, right? So pdv simply will be equal to 0. That means you can write du as ncv/dt. Now from here, like ncv/dt, you can write it like this, right? Now from here we can write h delta h as delta u, or delta u as ncv delta t. Delta u plus p delta t plus p delta p. Now here delta h. Now here, now let's write it like this. Delta p, like here. Now from here you can simply use the ideal gas equation now. So to use the ideal gas equation, so we know PV equal to nRT. So that means delta PV equal to nR delta T. As nR both are constant, right? So nR would be kept outside the change. So delta PV equal to nR delta T. Now from here you can write delta H equal to delta U plus nR delta T. Now delta U delta H is equal to delta U, you can write it as NCV delta T plus nR delta T. Now from here delta H we can write it as N delta T, you can take it as common, CV plus R. Now we already know Cp minus Cv equal to R. So C, that means Cp equal to Cv plus R. So this gives you Cp N delta T. So delta H equal to N Cp T2 minus T1. Okay. This is the change in the enthalpy of the system. Okay. So now, so we got the one term. We got like the first term, the change in first term of the Gibbs free energy. Now we will calculate the change in the entropy. Okay. So now for the entropy, what you can do, so entropy basically there is like more things can change, right? So entropy would be simply using we'll start again from first law, dq equal to du plus tw. So now here dq is basically tds equal to du equal to cv dt plus dw is P dp basically, because the pressure is changing, right? Now from here, what you can do, Ts would be simply Cv dt by T plus V by T into dt. Okay, now from here, we know we know that P is equal to rho naught P by N. So that means V by T will be NR by P. So we can substitute this thing here, which gives us Cp 3 by T plus NR P by T. Now if you integrate this will simply gives you like ds s1 to s2 Cv t1 to t2 minus p p1 dp. So this gives you delta is equal to r for n mole n cp ln t2 by t1 minus nr ln p2 by p1. Okay, so now from the problem you already know, right? T2 is simply 320 Kelvin, right? T2 is 320 Kelvin, T1 is 300 Kelvin, P2 is how much? P2 is 2 atm and P1 is 1 atm, right? P2 is 2 atm, P1 is 1 atm, right? So if you substitute all of this thing here, this basically gives you delta is simply, this is a monoatomic gas also. Monoatomic gas, for monoatomic gas, Cp would be Cv would be 3 by 2R. 3 is basically is like, so this comes because like there are 3 degrees of freedom, right? So like for a monoatomic gas in 3D, there are 3 degrees of freedom. It can like move in 3 different directions, right? For a monoatomic gas. For each direction there is half kBT, half kBT, half kBT degrees of freedom is there, right? So from the degrees of freedom, what you can do, you can calculate the internal energy, and from there you can calculate the CV, right, which gives you 3 by 2R basically. If you calculate the specific heat from the internal energy, internal energy gives you 3 by 2 kBT, and from there if you calculate the CV specific heat, that constant for 1 mole of gas, if you calculate it, you calculate this quantity, this basically gives you 3 by 2R. So now, so that is it. So now if you substitute all of these things here, so Cv is 3 by 2R, so substitute everything, 3 by 2 3 20 by 300 minus 7 it gives you delta is equal to, you calculate this whole thing, this simply gives you minus 4.42 per kilometer. Now we'll do, now this is the change in the entropy of calculated. Now the delta H we have to also calculate, right? Delta H. So delta H we have calculated previously, delta H. From here also we can calculate its Cp is like 3 by 2R, T2 by T1 is basically 320 minus 300, this gives you 15.7. So fine. So from here, delta G is already delta H minus delta S. So delta G will be 415.7 minus 320 into 4.42 will be approximately 0.5 joule. This is how you should calculate it, guys. Okay, the question number 4 is done. So how we have calculated? We know delta G as delta H minus T delta S. So in order to calculate the Gibbs free energy, we already know that we have to calculate both the delta H and change in enthalpy and T minus T delta S. So first, in order to do that, first what we have did, we have calculated delta H. Delta H equal to delta U plus P delta PV. From there, we got the expression of delta H. Delta is nothing but the CP T2 minus T1, and we know T2 minus T1. So from there, we have calculated change in the enthalpy. Now from the next step, using the second law, first law of thermodynamics, we simply calculate the change in entropy. So for that, we have calculated delta S ds. Here, as you can see, delta S we have calculated. Delta S value T2 T1, T2 P1 we have substituted. From there, we got a delta S minus 4.42. And after substituting both these change in delta S and delta H into this expression of the change in the Gibbs energy, to get the total value of the change in the Gibbs energy. So that's how you should solve the problem. So question number 4 is done. Now we'll go to the question number 5. Systems of atoms with energies equal to minus E0, 0, 0 is in thermal equilibrium at temperature T. Let beta equal to KVT inverse if beta is equal to 2, the probability of finding the system in the level equal to 0 is given x plus 0 minus 0 cos hx. Okay. So this is the problem. So the options, let me select the options. So universe 1 plus 2 efficiency was inverse option A plus inverse. So there are three levels of energy system, right? So let me just draw it over for simplification. So energies are at E0, 0, minus E0. These are the three energy levels. Now here the system is in thermal equilibrium at a temperature T. Okay. Now if beta E0 is 2, we will use this fact later. The probability of finding the system equal to 0. So this whole system is in thermal temperature T, beta is find the probability of being in the level E equal to 0. Now what you can do, you can simply calculate the partition function level. So there are basically three energy states, minus E0, 0 and E0. So for this case, the partition function would be e to the power beta E0 plus e to the power beta into 0 plus e to the power beta to minus E0. This gives you 1 plus e to the power beta E0 plus e to the power minus beta E0. This will be the partition function Z. Now, so from here, would be using this fact, okay, this thing here. So this thing is given, okay, this to the power x plus to the minus x will be cos hyperbolic x. So it use this fact, you can write z as z would be 1 plus 2 cos hyperbolic beta is 0. Right, you can like this thing, you can write it like this. Okay. So z is the partition function here. So you can write the z. So by defining it, you can calculate what is the probability of being in the state equal to E0. So for that, for equal to E0, what you can do? So at E equal to 0, the Boltzmann, because we know at any state the probability is like at state E, the probability of the particle would be P of E would be e to the power beta E by Z. Right, this thing we already know. Like we have, like in previous tutorials, we have already discussed this property, right? This is simply the probability, like by given the fact that the system is in thermal equilibrium. So for at E equal to 0, that means using this formula, you can write probability at equal to 0 would be simply e to the power beta into 0 plus z. This gives us 1 by 1 plus cos hyperbolic beta is 0. Right. This will be equal to 0. Right. This is the probability at E equal to 0. Okay. So this is the probability we got. So now the next thing is that B equal to E0 is 2. That is given in the problem. Okay. So for that, so we can substitute that thing also into the probability. So by doing that, we can write P equal to P as a function equal to 0 as 1 by 1 plus 2 into uh, cos 2 into cos hyperbolic 2, right? You can write it like this. So, so from there, probability of equal to 0 is this. So this will be simply equal to 0 will be simply 1 plus cos cos so this is actually, yeah, this is the okay. So let me tell you what is basically happening here. Oh. So there are basically three systems goals. Three energy states are mentioned in the problem. From there, you have to find what is the probability of being in equal to 0. For that, what we have first calculate the total partition function of the system. That is this sum of these Boltzmann factors, like for each of the energy levels. That we got like z equal to this because we have used this expression that is given in the problem. Okay. Now from there, you already know like the like for this kind of problem, the thermal equilibrium, the probability to stay at any energy level is given by this this probability of E by this formula. Now from here we have to put equal to 0 here. So if you put equal to 0 here, this gives e to the power minus beta 0, e to the power minus beta 0, beta put into 0, it gives e to the power minus 0, that gives you 1. By z is nothing but 1 plus 2 cos hyperbolic beta is 0. This is this. Substituting all of these things here gives you p e to the equal to 0 is this. So p equal to 0 is this. So that's how basically solve this problem. This is it. Now we'll go to the so now this is it. So now we'll go to the last problem. Okay, problem number 6. So problem number 6. So for problem number 6, okay, let's 6. According to the theory of equipartition of energy, system is in thermal equilibrium at temperature T T, then each independent quadratic term contributes, then each independent quadratic term contributes how much energy to the total energy value. Okay. So let me also write the options. So option A is RT by 2n, option B is PBT by 2n, option C is 3 PBT by 2n, option D is 3 RT by 2n. So four options are given. So for that, so we have to calculate the how much total energy will do. So how can we do that? Uh, so as we know from classical statistical mechanics that each term, each if there is for a 3D system, like for each degrees of freedom will contributes half kBT amount of internal energy. That we know from classical statistical energy, equipartition of the energy. So now we have to write like half kBT, that is already established. Okay, no. So that half kBT, but in the option there is no half kBT is given, right? So so we have to rearrange the terms in such a way that it will match one of these four options that are given in the problem. Okay. So that is the things we have to basically do here. Okay. So for that, let me first write in classical statistical mechanics. Change the program which will be forward quadratic theory of freedom contributes half kBT. Okay. Now to the average energy of the system. Okay. Now Kb already knows the Boltzmann constant, and J is simply the temperature. Now for n particles, the total energy contribution per particle, then the total contribution per particle per degrees of freedom is still half kBT of freedom. This is for a single particle. Okay, like if you consider what would be the degrees of freedom for n particle, that simply be n into half kBT. Okay. For single particle, this is for single particle. Okay. Single particle. Now, now what you can have to as I have told you, right? We have like this option is not given into the problem. So what I have to do? We have to rewrite this whole thing. Okay. So what you can do? You can know the ideal gas constant R as n into Na is nothing but the Avogadro number Kb. So you can write Kb as R by Na. Now if you substitute half kBT, so half kBT is there, you substitute kB here, so this gives you half RT by Na. Okay, so RT by 2n. Okay. So the correct answer would be RT by 2n option. So I hope how this thing is coming. Basically, you have to use this expression here, R equal to Na by kB. And from there you will get the kb as R by Na. Then if you substitute kb, half kBT, this gives you RT by 2n. So this is how you should calculate. Okay. So question number 6 is done. So so we still have some time remaining, around 25 minutes. So what we do, we'll do some extra problems. Okay. So we have still some time remaining, so we'll do some extra problems. So let me start. Okay. So, let's do this problem first. So some extra problems will do. A system of non-interacting Fermi particles with Fermi energy EF as the density of states proportional to delta E, where E is the energy of the of a particle. Now, by given that the average energy per particle at temperature T equal to 0 is average temperature is A minus 6 EF B 1 by 5 EF C 2 by 5 EF and D 3 by 5. So four options are there. Just Okay. So how to do this? First, what you can do, we have in general that the total number of particles. Okay, like these things that temperature equal to 0, right? This thing we have to calculate is at temperature equal to 0, right? T equal to 0, right? Now the thing we know, like at temperature equal to 0, if let's suppose this is the energy level. This is the energy level. Yeah, this is the energy level. This is the number of particles. As we know, at temperature equal to 0, the state up to the Fermi energy states are fully filled, right? And any states that is so the states beyond the Fermi energy levels are simply 0, right? That we have already know. Okay, so that is at equal to 0, right? So that means first what you have to do is the average energy per particles. Okay, so let's first calculate what is the number of particles is there. Now at t equal to 0, as you already know, say that the energy up to the Fermi energy levels are only get full, right? That is EF. So up to the Fermi energy levels are full. So what you can do, you can write the total number of particles n would be 0 to EF FE GE into DE, where F is the Fermi distribution function. Okay. This is the total number of particles. Okay, Fe G into D. Fe is basically the Fe is the distribution, Fermi distribution. G is the density of states, right? Density of states. Okay. So density of states is like is mentioned, right? Density of states is proportional to, here as you can see, the density of states is simply proportional to root under E. So from there, GE, GE that means would be proportional to root under E. Right. So now the total number of particles N would be 0 to EF AFE root under E GE. Now here F is a Fermi energy distribution. So now if you simply do this calculation in, this simply gives you F simply gives you function of EF into e to the power f 3 by 2. Right. Now, similarly, the total energy E can be similarly calculated 0 to EF E. Now here, the total energy E would be simply, that means 0 to EF. Now here E is there, E into FE GE DE. Here similar way, 0 to EF E Fe e to the power half dE, that simply gives you function of EF to the power 5 to 5 EF to the power 5 by this is coming because 0 to 0 if e to the power half plus 1 gives you 3 by 2 dE. So this if you do this simply gives you 3 by 2 1 by half 3 by 2 3 by 5 5 by 5 by 2. That is fine. So total energy E would be this, right? So now the average energy per particle, right? Average energy per particle will be simply this total energy E by N. That means three by two, this basically gives you E by N is basically gives you 3 by 5. Okay, so that means the correct answer would be 3 by 5. This would be the correct answer. Okay. So so this is how you should solve the problem. So what we have done here. So as you can see, the system, so the Fermi energy, so at T equal to 0 temperature, as we know, the systems are like for a Fermi energy Fermi system, the up to the Fermi energy level, the whole states are filled, and beyond the Fermi energy there are no states. So the total number of particles first we have calculated, which is given by this formula, F is into D. We have given G, Fe is the distribution function, G is the density of states, which is actually proportional to Tandaris, as mentioned in the problem. From there, we have first calculated the total number of particles, and then from there, we have calculated the total energy. Similar way, equal to E, Fe, G, D. Same we have calculated the total energy. So total energy basically gives you this. Now the question has been asked that average energy per particle. So that means what you have to do, the total energy you have to divide it with the total number of particles, which gives you 3 by 5 into 8. So okay, that's how you can calculate. Okay, the correct answer is given 3 by 5 into 8. Okay, so this is it. Okay, so so as you can see, we like this is it for today's class. So we have like discussed many things. We have started from like thermodynamics, potential, and all. And from there we have calculated like how the work done is happening on different types of systems using thermodynamic potential. We have derived it. Second is like similar types of problem, question number 2 also. From there we have like in question number 3 also have calculated entropy problems. Question number 4, and from question number 5 onwards we have done some statistical mechanics problem, where like the energy states, like particles are distributed in the different energy states. From there we have to calculate like different types of things, probabilities and all. And lastly we have also done one another problem on statistical mechanics, mostly on like Fermi particles, like how to calculate the Fermi energy levels, the energy per particles, all of the things. Okay, this is it. So that's all. So let me just conclude the class. Okay.